Hello everybody, and thank you for joining me today. As incoming President, I would normally welcome you in person to Birdcage Walk for my address, but unfortunately that's not possible this year. But I am delighted that you're able to join me online wherever in the world you may be. Firstly, thank you very much indeed for electing me as your 136th President. I've been a member of the institution for over 50 years, and this is obviously the highlight of that period. Our institution will be 175 years old in January, and many of the things I say today are set in the context of that history and the celebrations that we look forward to in January. The theme of my presidential year is innovation in engineering. In particular, how new ideas can be turned into new business. I recently spoke to Lord Bilimoria, the founder of Cobra Beer and today the president of the CBI, about his experience as an entrepreneur and an innovator. You'll be able to see highlights of our discussion later in my address. But first, I'd like to talk to you about how I got into engineering myself, what I've done in my career in engineering. I was very familiar with the word engineer from my earliest years. My father had served as a private soldier in the Royal Engineers in the Second World War. This is a picture of him carrying part of a Bailey Bridge somewhere in the North African desert. He's the tall one in front on our left. When his wartime pals came round to our house in the late 1940s and the early 1950s, which was quite often, they struck me as very practical people who could get things done. At the same time, I used to enjoy things like looking at cutaway pictures in the Eagle comic, messing about with Meccano and things like that. All classic stuff really for an 8-year-old boy. When I was 11, I won a school book prize, up to 10 shillings in value. I actually wanted one on train spotting, but that was considered unsuitable. So I was given this book, Men, Missiles and Machines by Lancelot Hogben. I still have it obviously, rather battered. It's interesting to look at the pictures of, for example, what we would now call renewable energy systems. The following year I got another one, and this time, of my own volition, I chose a book called 6 Great Engineers. 2 of the 6 were Charles Parsons and Christopher Hinton, both prominent members of this institution. In fact, the book contains a portrait of the Charles Parson identical to the one in our Parsons room on the first floor. Obviously by then, and this was at the age of 12, I'd made my mind up that I wanted to be an engineer. And on reflection, I felt that that was how I could personally do something useful and worthwhile in the world. This pattern continued during my teenage years, messing about with bikes and radios when it didn't interfere with schoolwork, cricket or golf. And when it came to that time, I chose to do engineering at university, or mechanical sciences as it was known at Cambridge. The course itself was quite theoretical and mathematical, although the engineering labs had some impressive kit, although by today's standards not much health and safety. This led on to my first job in the aerospace industry, which I'll cover shortly. But in terms of wider education, I'd always wondered about getting a business degree. It seemed to me that any engineer who couldn't understand business and finance would be fighting with one hand tied behind his or her back. So when I was working in Scotland at about the age of 30, I took an MBA on a 3-year part-time basis at Strathclyde Business School. Another 10 years on, my company sent me to the International Senior Management Program at Harvard Business School in Cambridge, Massachusetts. This was a 2 to 3 month, 6 days a week intensive course. The teaching structure was very interesting, all done by case studies with 2 or 3 cases per day, and with students being called at random in the class to give 5 minutes on what they would do in the circumstances of the case. And quite often the head of the company in question would come along and say what did actually happen and whether it had been successful. We had inputs from Nike, Asahi Breweries, General Electric and Pilkingtons, to name a few, as well as lectures from well-known names such as Michael Porter. Overall, if asked to give advice, I would say that the business education I was fortunate enough to receive counted for at least as much as my engineering education. And it's been particularly relevant to the work I've done in recent years on the finance board of this institution. In terms of my industrial career, I spent just under 40 years developing and making products and supporting them, working for 4 companies: BAE Systems, Leyland Trucks, ABB, and a small company owned by a private equity firm. I started on basic design and development work on the Anglo-French Jaguar aircraft project, and then gradually acquired more and wider business responsibility, and I had about 15 years in general management and managing director type roles, with quite a strong emphasis on international work and quite a wide variety of experiences. I then had about 10 years working at the interface between business, government and universities, something which happened rather by accident. I was appointed to act as project director for setting up the Manufacturing Technology Centre near Coventry, and I did some similar work for the Manufacturing Catapult and for the Aerospace Technology Institute. These were all start-up situations which needed some clarity of purpose and vision, particularly to carry them through the early stages of skepticism and doubt. In all, I've always felt that I've had quite a varied career, and when I reflect on learning experiences, it covers a very wide range of things. At the core of much of it was how to develop products and make them reliable and cost-effective. At the same time, you have to know how to get money, you can't do much without it, how to deal with company, employment and contract law, hiring and firing people, taking over and being taken over, being made redundant, and working with a wide range of nationalities, and very occasionally meeting royalty. And also, very occasionally, being driven on 2 wheels for about 3 miles. This isn't a trick photo, by the way. That's me sitting in the passenger seat with a French guy, Gilbert Bataille, at the wheel. But the overall message from this is that the skill that any competent manager needs is the ability to get things done, despite the above, and get a result. Much of it seems to have little to do with engineering, but this should not come as a surprise, as engineering is all about turning invention and technology into something useful, and that means interacting with the real world. So if there is a common factor from all this, then it's the constant pursuit of innovation, whether that's innovation in technology, products, services or processes. So what is innovation? Well, in the 16th century, you might be interested to know that innovators were religious heretics with strange and unacceptable ideas. So, for example, Edward VI in 1548 issued a proclamation against those that doeth innovation and threatened them with His Highness's indignation, imprisonment and other grievous punishments. And Edward, by the way, was only 10 years old at the time. So if there are any innovators listening today, you'd better look out. Today, innovation in its various forms is highly prized, and to many is the ultimate driver of economic growth. So we find, for example, the 20th century Austrian economist Joseph Schumpeter, who was a professor at Harvard Business School, concluding that long-term growth was sustained by waves of creative destruction, so-called, based around innovation. And whilst innovation might destroy the value of established companies, in the short term, it ultimately results in greater long-term growth. And Peter Drucker, who's a personal favourite in management thinking, identified innovation as a powerful force, but one which arose more from analysis and hard work rather than pure inspiration. And he identified 7 sources of innovation, of which new technical knowledge was one of the most powerful, but also the most difficult. Lord Bilimoria is an inspiring example of someone who has combined innovation with entrepreneurship. I spoke to him recently to hear his views on how we can encourage innovation and how more engineers could be encouraged to become entrepreneurs.
manufacturing accounts for 10% of our GDP, and I'm proud to chair the Manufacturing Commission. And I am in my own business with Cobra Beer, which I'm the founder of, and I'm chairman of a joint venture we have had now for over 11 years with Molson Coors, the largest brewers in the UK and one of the largest brewers in the world. And I'm a proud manufacturer. And 10% of GDP sounds small, but it's actually a very large percentage and proportion of our economy. And the manufacturing we carry out in the UK is world class.
Yes.
We are fantastic manufacturers in a variety of areas, from aerospace to automobiles to beer. And we are very, very good. And when it comes to productivity, we have a productivity challenge in the UK. However, with our leading companies, including our leading manufacturers, our productivity is best class in the world.
How do you see innovation fitting into that situation?
To me, the best way to predict the future is to look to the past. And if you look to the past of the UK as a country, one of the reasons why today, with just being 1% of the world's population, we are still one of the 6 largest economies in the world, is because of our historic ability to be truly creative and innovative in every field you can imagine. Whether it's sports, just about every major sport has been invented in the UK, or whether it's engineering or manufacturing. We have been phenomenal, and to this day we are leading in the world. I mean, we are 1% of the world's population, but we produce 16% of the leading research papers. It's a British university that has won more Nobel Prizes than any other in the world. It's not an American one. It's not Harvard or Yale or Princeton or Caltech. It's Cambridge University that's won over 100 Nobel Prizes. So I think we are very good and historically have been excellent at being innovative, groundbreaking, world-changing innovation. And we're doing it as we speak. Today, in this pandemic, which is now almost a year ago that we started our first lockdown on 23rd of March, look at the amazing innovation that has taken place around the world, including in the UK. No better example than the Oxford AstraZeneca vaccine, which is a leading university, one of the best universities in the world, working along with and partnering and collaborating with AstraZeneca, one of the largest pharmaceutical companies in the world, a Swedish-British company headquartered in Cambridge. And then you take it one step further, collaborating with the Serum Institute of India, owned by the Poonawallas, Cyrus and other Poonawalla, based in Pune in India, the largest vaccine manufacturers in the world, who have a 1 billion dose contract with Oxford AstraZeneca for the vaccine. And that was at speed, when vaccines normally take decades to develop, or sometimes are never developed because they don't work. We have managed to do this at speed. And I think that is the best example of innovation you can, and it happened because of collaboration. We need that collaboration between government, universities, and business. You put that all together, it's very powerful. Well, again, with the Institute of Manufacturing at Cambridge, where I was proud to chair the Cambridge Arch Business School for 5 years, we worked very closely with the Institute of Manufacturing. And it is all about working collaboratively, even within a university framework, a university like Cambridge, where you have the engineering department, which to this day is the biggest department at Cambridge University. I know some of the lectures that I've given are in the engineering department lecture hall that can seat 400 people. It's the largest lecture hall in the university. And so it is such an important department. But again, it's that collaboration. And even at the Institute of Manufacturing, I've seen innovation is at the heart of what they're doing, to the extent that the head of the Institute of Manufacturing, Professor Tim Minshall, is also the first professor for innovation in the university's 800-year history at Cambridge. Well, our universities are a jewel in the crown of the country, and we have the best universities in the world, along with the United States of America.
Yes.
And there's no question about it. Our professional qualifications as well. Our institutions, like the Institution of Mechanical Engineers. I mean, we have world-class institutions. These are not things that you can just switch on in a moment. These have been built up in many cases over centuries. And these institutions give our country and our economy and our businesses phenomenal strength and depth that helps us with our global competitiveness. And they are, as you say, recognized our qualifications around the world. So those letters after the name are respected. If you're a scientist, if you have FRS after your name, that is you've reached the pinnacle globally of being a fellow of the Royal Society. So, and I think it's very, very important that we, in our global Britain, which the government wants to champion, we need to have that confidence and shout from the rooftops about the strengths that we have, including our institutions and our universities. And of course, the international students that come and study in our country bring in £26 billion directly and indirectly to the economy. But far more than that, they are the strongest element of soft power. There are more world leaders who've been educated at British and American universities than any other country by miles. And the generation-long links that are built through foreign students, international students, is amazing. And that's the other aspect of Britain, is we have the strongest element of hard and soft power combined of any country in the world. And that hard power, our engineering capability, our manufacturing capability, combined with this phenomenal soft power that we have in every aspect, makes us very, very competitive globally. I do believe that underlying all this, people don't appreciate enough, is that the most important aspect to be an entrepreneur is the ability to be creative. And it's that ability to be creative that generates this innovation, that generates products that are different and better, and are quite often game-changing or world-changing. And that's the same thing about engineering. Yes, it's a discipline where you have to learn the skills, but really good engineers are very, very creative. And the best part about it is you then engender trust. And a professor of mine from Harvard Business School, in the middle of the pandemic, gave us a lecture to cheer us all up in the middle of the pandemic. And her message was all about trust, and said, to get trust, it's a triangle. First, you've got to be authentic. Next, you've got to have the logic. Do you have the capability to deliver what you say you're going to do? And you have that expertise and capability. And finally, do you have the empathy? And if you're authentic, you have the capability, and you're empathetic, you get trust. And I think our engineers have all those three things, and they are trusted around the world, and something we should be very, very proud of.
So from what we've just heard, innovation is a powerful but somewhat unpredictable force. And these are points which the institution should bear in mind when it's asked to advise or comment on engineering policy matters. Always stressing, of course, the element of unpredictability. The natural tendency when thinking about innovation is to consider the headline-grabbing top 10 developments. So, for example, we think of Thomas Newcomen, the Stephensons, Frank Whittle, Shockley, and perhaps more recently, Elon Musk. But when you consider the developments of this type and their impact, it's hardly surprising that governments the world over put money into what they hope will be the next major breakthrough. But the reality, of course, is that whilst most engineers spend their working lives doing innovation, most of it results in modest but extremely useful improvements. That's why, for example, Model T Ford in 1908 cost about the same in real terms as a modern car. And it's also why computers have shrunk from the size of a house in 1945 to the size of a pin or less. And it's also why golf clubs hit the ball so much further, at least in the right hands. So in the developed world, nations typically spend between 1% and 4% of their GDP on what is described as research and development. In this context, R&D means the activity that typical engineering companies carry out. It might be considered a rather narrow definition of innovation, excluding, as it does, innovation carried out, for example, in service companies. In parallel with that, we see patent applications growing at about 5% a year for quite some time. And economic returns from R&D can also be very substantial. Private returns to companies are typically between 10 and 30%. but much higher when spillovers are included. However, the returns from one particular investment or one project are much more variable, of course. It's for these reasons that governments the world over are supporting innovation. Here in the UK, for example, the UK government is trying to increase spending in this area from the current rather modest 1.7% of GDP to 2.4%, which is close to the OECD average. The UK, by the way, does rather better on other measures of innovation. We also see direct encouragement to innovation through initiatives such as Innovate UK, the Catapult Network, and the Aerospace Technology Institute, some of the things which I've been personally involved in. Our institution also has, in its own modest way, played its part in encouraging innovation through, for example, the Manufacturing Excellence Awards we've been running since 1982, and now with the Manufacturer magazine under the TMMX banner. Then there's the Stevenson Fund, where we've invested £1.7 million of the institution's funds in 11 early stage companies, and through the various student and apprentice challenges which we have in the fields of apprentice automation, rail, autonomy, design and motorsport. So innovation is clearly good for everyone, and it's very much the stock-in trade of engineers in their everyday lives. Is it easy to do product development, which is arguably the engine of innovation? Well, those of you working in this field will know that technical innovation is a powerful but difficult activity. Perhaps this is because expectations are so high. It's difficult in a new environment to reproduce the standards set in established industries such as automotive, aircraft, consumer goods, in terms of, for example, cost, safety and reliability. In the literature and the teaching, there's been relatively little coverage of the processes by which engineering products are created and how they are developed to meet these expectations. So it was on this basis that I put together my own thoughts in a book I had published in 2019 entitled Managing Technology and Development Programs. We're taught academically lots of engineering theory and analytical skills. And most of us have been through some form of practical skills development. If you're interested, we can undertake business education, as I've done myself. But we're not taught how to develop technology and how to turn it into reliable products. Quoting again Peter Drucker, he drew attention to this topic in 1985 when he said, "We know how to train people to do technology such as engineering or chemistry, but we do not know how to endow our managers with technological literacy, that is, with an understanding of technology and its dynamics." Yet technological literacy is an increasingly major requirement for managers. Without going into too much detail, my view is that engineering development revolves around the concept of technology maturity, a concept first developed by NASA in the 1980s. New technology, unfortunately, does not just jump out of the box ready to go. In fact, quite the opposite is true. It starts full of promise at the early infant stages in the laboratory, is only mature when it can be made in quantity, economically, and working reliably. The middle section is often the most difficult, a little bit like teenage years in human development, which many parents would prefer to omit. Something that gave the impression of being a good idea in the laboratory turns out to be difficult, temperamental, and recalcitrant. You can't miss this part out, but with patience, good results can be achieved. Other key concepts are the idea of engineering being an iterative and learning process, where the right first time concept doesn't apply, or at least not quite in the form understood in manufacturing. There are also the concepts of risk being reduced progressively over time in a development program by a wide variety of methods. But the cost of failure and remedying problems gradually increases over time. The trick obviously being to do as much upfront as possible. Time doesn't allow me to go into too much detail, but a well-formed process for turning innovation into products would cover, for example, the core development process itself, concept development, aligning with business and manufacturing strategy, risk identification and reduction, validation, producing engineering data, managing the work, and how to get funding. And then, of course, the core skills needed to underpin all this. Quite a formidable list of things to do, but also quite indispensable, and confirming that this is a real and complex process. My own thoughts on this are explained in rather more detail in the written paper I've produced for this address. So let's move on now to the role that innovation and engineering will play in the future, but starting with some context and reflecting on what's happened to technology and innovation since the founding of this institution. We were very much at the forefront of the first industrial revolution, and we're arguably now in the middle of the fourth one, driven by data, intelligence, and analytics, but not supplanting the old physical technologies, just making them work better. In the 175 years from 1847, we've seen the annual production of many of the things we take for granted rising from nothing to the figures you see here. 93 million cars a year, 1.5 billion telephones, 25,000 terawatt hours of electricity. And this process of growth was driven by new technologies and new products. Products which were successful in meeting customer demand, and in the process creating wages for those who made them, in turn creating more customers. A virtuous circle where they have become increasingly affordable from improvements in efficiency and in productivity and in capital intensity and so on. At the same time, the world is improved immeasurably in other respects, despite opinions to the contrary. For example, world health has improved radically when measured by life expectancy, infant mortality, or extreme poverty, as well as the elimination of certain killer diseases. In the case of my own family, in 1847, my great-great-great-grandfather, Patrick Flinn, and my great-great-grandfather, also Patrick Flinn, were living in a tenement building, a court so-called, in central Liverpool, with 2 rooms, a family of 10, no toilets, and no running water. So few could argue that the world has not improved much since 1847, and a lot of that improvement is down to engineering. But at the same time, we have the uncomfortable fact that the concentration of carbon dioxide in the atmosphere has risen from about 284 parts per million to 412 in 2019. So whilst engineering was painting very much on a blank canvas in George Stephenson's time, the world is a much more demanding and complex place with some heavy challenges. Whether those challenges are greater or lesser than those in 1847 is a matter of debate. Many challenges, in fact, were there in 1847, but in worse forms, but accepted as facts of life. But in this context, the United Nations has identified 17 sustainable goals, development goals, which cover a wide range of topics. 5 of today's goals are particularly relevant to us as engineers. Things like clean water and sanitation, affordable and clean energy, decent work and economic growth, industrial and innovation, and responsible production. These also align with the fact that many national governments have committed to net zero carbon targets by about 2050. Our natural tendency as engineers is to think of technological solutions to these challenges. And in particular, of the high level of integrated systems such as power plants, automobiles, and the infrastructure systems. But these are only enabled by intermediate technologies such as batteries, carbon capture, and electric motors, which in turn are supported by materials technologies. These then need to be brought together using data and information systems managed as a whole entity. The point I'm making is that solutions to these global problems need to be managed holistically and not as a series of discrete or separate interventions. Systems integration in its widest sense is probably not given the prominence it deserves, which then brings us on to the point as to whether are we actually doing and spending enough. The world is certainly spending a lot of money on the R&D which might support these developments, something in excess of $1 trillion a year, although expenditure in the UK is below where it ought to be and is concentrated in about half a dozen sectors. But it's been estimated that in the UK, to resolve, for example, climate change problems, we only need to spend 1 or 2% extra on GDP on all forms of investment, which doesn't seem a lot, given that nationally we spend somewhere between 15 and 25% of GDP each year on all forms of investment. And there's no shortage of cash. The world's top 3,000 companies, for example, are sitting on about $7.6 trillion of cash at the present moment. And in 2020, companies raised somewhere around $3.6 trillion of new funding. But the most attractive investments seem to be those which feature words like cloud, health, and digital. So one question is whether enough is going into other challenges such as climate change, and whether the economics of climate change solutions are attractive, bearing in mind that a lot of the money I've mentioned is made up of our personal savings. So overall, I think we have a three-pronged challenge. Obviously to develop technical solutions, but then to match those first with what customers and markets actually want. Secondly, to attract the funding to make those things happen. My overall conclusion is that many, if not most, of the world's challenges can only be solved by engineers, a factor that is sometimes overlooked. However, given the progress we've made since 1847, we should be optimistic that solutions will be found in a timely manner, provided that those solutions are managed holistically, integrating all the relevant factors. So let me move on now to the implications of all this for our institution and what it does. Of particular importance is the effectiveness of engineers in doing innovation work, with a focus on the topic we've just discussed, and hence improving general well-being. At its founding, the purpose of our institution, that is, what it stands for, was stated to be, for example, to meet and correspond, to interchange ideas, to increase knowledge, and so on. It's notable that right from the outset, the institution had two distinct aims. Firstly, to help engineers develop and increase their knowledge. And secondly, to help society through useful, a word with very practical connotations, engineering. Over time, the words have evolved. For example, at the time of granting of the Royal Charter 90 years ago in 1930, or of charitable status in 1963. Nowadays we use the phrase improving the world through engineering as our statement of purpose. These are words that might be described as the external purpose of the institution. Internally, its role continues to be to help engineers in their personal development and in their careers and in their general effectiveness as rounded individuals who can fulfill their own aspirations and contribute to the general well-being of society to the best of their ability. Mechanical engineering, of course, is not a static subject. We still have intrinsically mechanical devices such as cars, or trains, or ships, or aeroplanes, and machine tools. But over the last 40 to 50 years, these have all become more complex as they've acquired intelligence, which has enhanced their performance in a variety of ways, although we still don't have the levels of reliability from software as we do from physical devices. The expectation is that we will make greater use of data over the years to come, which will add further to professionalism of maintenance and, for example, support activities, as well as providing better design data. So with those thoughts in mind, my view is that immediate priorities for our institution should be in these areas. We need to provide thought leadership in engineering technology, both to our members and to policymakers and society at large. We need to increase the reach of the institution, both internationally, but also perhaps into areas such as operations and maintenance, where people have not traditionally seen themselves as members of professional institutions. We need to develop offerings, our value proposition, so that it meets the needs of a wide variety of people at different stages of their careers. And finally, we need to continue the journey we've been on for some time now to deliver many more of our services digitally. And to underpin those points, we clearly need an institution which is financially resilient. IT systems that supports the points I've made, and our building. It's 122 years old, for many the epitome of the institution itself, but it needs substantial money spending on it. And finally, we need to embed the many changes we've made recently to the governance and management of the institution. So in conclusion, what would I say? Well, first of all, that I decided personally at quite an early age that I wanted to be an engineer, and I felt that it was a useful vocation to follow. And it's certainly been a profession which, from my point of view, has brought a rather more varied and more interesting life than perhaps I expected. And I can also look back with interest on products that I've worked and are working quite well, and I've given my views on how that might happen. I've also more recently seen some new organisations set up that have continued to flourish. And this is all about turning ideas into something useful and affordable. After all, as was observed as long ago as 1847, an engineer can do for $1 what any fool can do for $2. So I hope that in the course of this year, I can help the institution to grow and to become more influential in the outside world. And in particular, be a welcoming and supporting organisation for all our members. Thank you once again for joining me today. I'm always open to questions, and you'll find more details of what I've set out today in my published address. Thank you.